right, so I'm going to be honest with you. The first video I did on vectors on the plane I felt was way too long. So I'm just going to try to do a shorter video so that it gives you the basics of what you need to know, the bottom line of what you need to know to do vectors on the AP Calculus exam and any vectors you might need to know in the future. Okay, so having said that, I'd like you to get your calculator out because I want us to talk about how we would graph vectors in parametric mode, okay, on our calculator. So I have a handout here, and I'll give you a few seconds to get your calculator out, obviously. All right, and I've got mine out, and you'll be able to see it, which is really nice. I got it so that it's not shaded or anything, and that was quite a feat in and of itself, okay? So I'm going to go to y equals, and I'm going to clear out the two functions I had in there. And I want you to notice that when we go to diamond y equals, after we're in parametric mode, and remember you change your mode by hitting the mode key and changing it to parametric. So diamond y equals gives us where we would input our functions into parametric mode. Okay, so our vector valued function, which they define in calculus as r of t. Now, I don't really have an explanation as to why it's r of t versus x of t and y of t, except for the fact that oftentimes they'll define the x coordinate here as x of t times I, right? And then plus the y coordinate, which is y of t times I, or times j. So they needed another variable. S was taken for two-dimensional position functions, or I'm sorry, one-dimensional position functions, and now so we have r of t. So I guess it was the next letter after r, I mean s, so it was r, okay? All right, so what we're going to do is we're going to type our functions into our calculator, okay? So in the x coordinate spot, you're going to type in t, and please note that if you're multiplying two functions together on the TI-89, you have to use the multiplication symbol or it gets fussy. So second cosine of t, enter. And then we're going to enter the y coordinate, which is going to be t times the sine, second sine of t. And we've got that entered, okay? And then we're going to adjust our window, okay? Because I want us to have the same viewing window so we can see some pretty cool stuff happen here. So we're going to go diamond window, and then I'm going to change it to all these values. Now, please note that this 25 number here is just 8 pi in disguise. Okay, so we're going to have our t min, which is our parameter, and then t max, which is 8 times second pi, which you can just type in. And then we're going to have x min, or the t step, I would just keep as 0.1. And that's how often it's going to plot points. So you have a nice smooth curve versus a jagged one. All right, so we're going to make x min negative 20. We're going to make x max 20. We're going to have it in, the scale is in increments of 5. Y min will make negative 10. And y max will make 10, and then we'll have the y in increments of 5 also, okay? All right, so now we're going to do diamond graph. Make sure you're in radians, and let's see what happens. I love peanut butter sandwiches from Sesame Street, right? And we get a nice, beautiful spiral, okay? But you notice it was moving, okay? And I'm going to change my page here so you can see this. And there is the spiral, which is really, really pretty cool. And mine matches this spiral. Yours should match it too. Okay, now, this vector valued function is an interesting character here because at time t, this vector is pointing at where you are at time t. So at some time t, we're at this location right here. So it's pointing to where you are on the path. okay, at time t. So these are position vectors pointing to where we are on the path, okay? So like this would be r of, I don't know, sometime t sub 1, 2, 3, 4. So that's the fourth time, right? So the tip of this vector here is the path of your function. And it, so that's pretty cool. All right. So I wanted to make sure that we knew how to graph vectors parametrically on our calculator. Now, having said that, do you notice here that we have a curve? And curves have rates of change. They have slopes. So we need to find slopes, so we need to find tangent lines, and we need to find out where the tangent line's horizontal, where the tangent line's vertical, and all those calculus things with a vector valued function. And I'm going to talk about the calculus of vectors, and let's do a summary page of things that we need to know in order to work some problems. I'll work a few problems, and then hopefully this video will be a lot shorter than the first one I did. Okay, all right. So the calculus of vectors, what do we need to know? Well, we know that you have position vectors. And those are typically r of t, written as r of t. And you can use the ij language, as I just indicated when we wrote that a second ago, or you can just, use the angle brackets here and go x of t, y of t. Okay, so that would be the position vector at time t equals whatever time you want. All right, then we have a velocity vector, which we're going to write like this with a v. And believe it or not, it is going to be the derivative of the position vector. And that's going to be the rate of change of x, which is dx dt, comma dy dt. And those will be the components of the velocity in the x direction and then the y direction. And yes, we have an acceleration vector. Which would be a, which, you guessed it, is going to be the second derivative of position, or the first derivative of the velocity. And you would write it like that. And yes, there is a jerk vector. Which we're going to call j of t, and that's going to be the third derivative of position. Oops, the 3 goes in here. All right, and these are just the component parts for each one of the vectors, okay? Now, vectors have magnitude and direction, which is, classic vector vocabulary. Now, there's an important scalar that we need to know when we're talking about the calculus of vectors, and that's the speed. So speed, remember, is a scalar. What does that mean? It doesn't have any direction, it's just got magnitude. And that's going to be a function of t, typically. And that's just going to be the magnitude of the velocity vector. Well, what is the magnitude of the velocity vector? The magnitude of the velocity vector? Well, it's how do we find magnitude? Well, that's equal to the square root of the component parts squared. So that's going to be dx dt quantity squared plus dy dt quantity squared. And that would be the definition of speed. And you'll notice that it's the positive square root, and it's always positive. And this is just going to give you a number if you are at some value of t. Okay? Now, what else do we need to know in calculus? Well, I like to discuss the velocity vector a little bit, because the velocity vector describes motion. Now we're used to dx dt here is going to be the rate of change. Can I spell change? No. The rate of change of the x component of position, right? It's the rate of change of x. And then dy dt is going to be the rate of change of the y component. All logical, all logical. But what's a little bit different than the one-dimensional motion that we're used to, okay, is that the particle's going to be moving left if the dx dt is negative. It's going to be moving right if dx dt is positive. It's going to be moving up if the dy dt is positive, and down if the dy dt is negative. So you're going to have two, pieces to your motion. Okay, so when dx dt is greater than 0, we're moving right. Dx dt less than 0, we're moving left. Okay, what happens when it's 0? Well, it's not moving in the left-right direction, so it's not moving horizontally. And I didn't leave myself enough space here. So you can be moving right horizontally, left horizontally, or not moving at all horizontally. So let's do the same thing with dy dt. If dy dt is 0, you're not moving. The particle is not moving vertically. If dy dt is greater than 0, you're moving upward. And if dy dt, whoops, I forgot the 0 here. If dy dt is less than 0, you're moving down. Okay, so moving up, down, and not moving vertically. Okay, now, the question is, when is your particle not moving at all? The key difference between one-dimensional motion and two-dimensional motion in calculus is the particle is at rest when both dx dt and dy dt are 0. And I've got an and there, which means they have to be 0 at the same time. Okay? Because you can have motion in the x direction and you can have motion in the y direction and not have motion in the other two directions, So if your dx dt is 0, but your dy dt is positive, that means you're moving up, but not left or right. So they have to both at the same time be equal to 0. That's a key thing to know. All right. We'll talk about speeding up and slowing down later. The next thing we need to know is, obviously, I said our graphs have slope. We got to find the slope. The slope of a vector valued, I can't spell valued, function. Well, slope is as it always is, and that's dy dx, which is nice, right? The change in y over change in x. And just like we did slope parametrically, what we're going to do is we're going to take the y component of the velocity, which is dy dt, and we're going to divide by dx dt. And let's see if that makes sense mathematically. If, let's say we're particles moving in meters per second. So dy dt would be in meters per second, dx dt would be in meters per second. And guess what happens to the units? They go away and we just get slope. Okay? So to find the slope, you have to put the y component of velocity over the x component of velocity and evaluate at some time t. All right? And then what if I want to know the point? Because we want to find equations of tangent lines. And we'll say the point at t equals a. All right? Well, remember, a vector valued function, here is my cool vector valued function. The r is going to be pointing at where we are at time t. Because it's going to be in standard position at the origin, and it's going to be pointing to the path. All right, so if I want to know what the point is at t equals a, I find the vector value, or the position vector at t equals a, and that's just going to be x of a, y of a. And that means it's pointing to the point x of a, y of a. So if I wanted the tangent line, I would just say y minus y of a equals the slope, whatever we calculate, equals the slope times x minus x of a. And that's how I'd find the tangent line. Okay, so that's pretty self-explanatory. Okay, now the other thing we need to find typically we like to know when is the tangent line to r of t horizontal. Well, okay, so when do we know when we have a horizontal slope or a horizontal tangent line? When that's when the dy dx is equal to 0, but dy dx is dy dt, as I just mentioned, over dx dt. And this is going to equal 0 when the numerator is equal to 0. So horizontal tangent lines occur when dy dt is equal to 0, which is just the y component of the velocity vector. So when the y component of the velocity vector is 0, then we're either at a high or a low spot on our path. Okay? And then similarly, we like to know when is the tangent line vertical. Well, that's, again, when dy dx is undefined, right? So dy dx would be undefined. If you look at the fraction above, if we look at this fraction above, we can see that it's undefined when dx dt is equal to 0. Okay, but on parametrically or vector defined functions, what's interesting about having a vertical tangent line is that's going to be a maximum that I'm left or a maximum that I'm right horizontally, right? You see how dy dt is going to give you a maximum in the y direction. You're going to get a maximum with your vector valued. I really can't call them functions, right? Because this is a relation. You're going to have a maximum distance away from the origin, or the x, or from the origin, or in the horizontal direction. But so I find that very interesting, and you can find those points, which in time, which is pretty cool. All right. So that's an important thing to know in calculus. All right. So we've talked about position, velocity, acceleration, jerk, all being vectors. The speed is the magnitude of the velocity vector. We've talked about dx dt being the rate of change of the x component, dy dt being the rate of change of the y component. Particle is at rest when both of those components are zero at the same time. The slope of your curve is going to be when dy dx is equal to dy dt over dx dt. And now we know how to find when we have a horizontal or a vertical tangent to your curve, okay? Well, that's great. But now we got to talk about a subject called distance traveled versus displacement. So I'm going to talk about distance traveled first because that's easier, in my opinion. Distance traveled. Okay? And this is a scalar because it's a number. It's how far we went. Okay? And this is going to be over a time. And I'm going to call this time 1 to time 2. Well, that's just equal to, and if you think about it, in terms of arc length, this is dx dt, and this is dy dt, and this would be ds dt. Okay, and so how far I have gone is how far I went in the x direction and the y direction using Pythagoras, right? And I can say that ds dt is equal to the square root of, because it's a right triangle, dx dt quantity squared plus dy dt quantity squared. And I ask you why? Ha ha ha, that looks familiar. I've seen that before. Where have we seen this before? Well, Mrs. Muller, we saw that. That is the speed. It is the speed, but this is only a little bit of the speed. We want all of this, this speed. So what do? Is you sum from time 1 to time 2 the magnitude of the velocity vector, which is dx dt quantity squared plus dy dt quantity squared dt. Now let's see if that makes sense. We said that this right here, this is going to be in meters per second because it's, or some unit over some time. Okay, and so this is going to be units per some time. And then what happens is, since this is speed, I multiply it times time. What do we get? We get units. So the units work out here, okay? So this is the distance traveled, and it's a number, it's a scalar. All right? So then what's the difference between that and the displacement vector? Well, I'm going to harken back to my graph here of my curve, my velocity valued curve. And I'm going to have my position pointing to here. So I'm going to say this is R of T1. I don't know if you can read that, but R of T1. And then this is going to be R of time 2. So my particle is rolling along its little vector roller coaster here. And the displacement is going to be this vector right here, which is how far the particle was displaced from this point. So this is going to be the displacement vector, which I like to call I like to call this the R vector T2 minus R of T1, which is kind of like delta R. Okay, well, how do we find delta R? Well, that's a net change, isn't it? Well, net change Sounds like an integral to me. And it sure enough is. And that's equal, and I'm going to put this from time 1 to time 2 again. That's going to be the vector, which will be the integral from time 1 to time 2 of what? Well, how did I move? Well, this is going to be dx dt. Or I'm just going to say the velocity, if you don't mind. Velocity in the velocity x component. And then the integral from t1 to t2 of the velocity in the y direction. Okay, and this basically is the change in the x, and this is the change in the y component, which is, interesting. Okay, so this is the displacement vector. And I like to say that this shows us where the particle moved from and ended up to. So moved from here to here. And so you're going to have a vector that's pointing to where the particle moved. Okay, so that's the displacement vector. Okay. All right. Last thing I want to say about the calculus of vectors is oftentimes we need to talk about, if I'm given the velocity, how do I find the position vector? Okay. And if I'm given a velocity vector, and I have some function of x, and then I have some function, the velocity has an x component and a y component. Let me just straighten out my language there. Okay, and I'm given an initial position. That means r of, I'm going to say sometime a. Well, what is that going to be? Well, that'll be x of a, y of a, right? That's my initial condition. Can I spell initial condition? No. That's my initial condition. So what is the position function going to be? The position vector is going to be r. Old habits are hard to break. Is going to be equal to my initial condition, which is x of a, plus the net change of my x component here. So that's going to be the integral from a to some t of v of x dx, right? Because I got to use a different variable here. I've got way too many x's here, comma, the initial condition in the y direction of v of y of a plus the integral from a to some t of the velocity in the y direction. So it's like two accumulation functions here. So you're accumulating your x, how far you're going in the x direction and how far you're going in the y direction, and adding it to where you started. And this would be the position vector for that, okay? All right, that's a lot of words, so let's do some action here, okay? So I'm going to do an example really quickly here. It's called example 5, but it's really example 1. Okay, so let's remember that this is example 1. And my charge is going to be to find the acceleration, velocity and acceleration vectors for part A here. Okay, so part A is pretty simple. The velocity vector here is going to just be the derivative of the component parts. So we're going to take the derivative of 3 cosine t, which is going to be negative 3 sine t, comma, and I'm just changing to my nice angular braces. I like those a lot better. And then the derivative of 3 sine t is 3 cosine t. Easy points. And then a of t the acceleration is just going to be the derivative of the velocity, which is going to be negative 3 cosine t, and then negative 3 sine t. Easy enough. So we have position, velocity, and acceleration. And part B says, find the velocity, acceleration, and speed and direction of motion at pi over 4. So I want the velocity at pi over 4, which means I'm just going to plug pi over 4 into this velocity vector. So that's going to be negative 3 times the sine of pi over 4, which is root 2 over 2. And the cosine of pi over 4 is root 2 over 2, so this is 3 root 2 over 2. That's easy. The acceleration at pi over 4 is equal to negative 3 root 2 over 2. And the sine is root 2 over 2 again for pi over 4. So easy. The first 4 computations are easy. Now the speed. The speed is the magnitude of the velocity vector. So the speed at pi over 4 is the magnitude of the velocity vector at pi over 4. Well, what does that mean? We're just going to take the square root of the component parts squared, which means I'm going to say negative 3 root 2 over 2 quantity squared plus 3 root 2 over 2 quantity squared. And that's going to equal, that's 9 times 2, which is 18 over 4, which is 9 over 2. So this is the square root of 9 over 2 plus 9 over 2 because they're the same. I'm doing math in my head. That can be dangerous, as you all know. And that's 18 over 2, which is 9, which is 3. So the speed at pi over 4 is 3. And notice that's a scalar. That's a number. That's what we expect, right? And the direction. Well, the direction can be done one of two ways. You can do the angle of your velocity vector. Okay, so my velocity vector is, if I were to do the quadrant, it's going to be negative, positive right up here. So this would be my direction angle, theta. And this looks to me like it's this magnitude here is 3, and then my root 2 over 2. So I think theta here is 3 pi over 4. I think everybody can see that because the velocity is equal to 3 if I pull the scalar out, negative root 2 over 2, comma, root 2 over 2. And this is in quadrant 2, and it's the pi over 4 angle, and it's going to be pi over 2, 3 pi over 4. Okay? And we can also use the unit vector to, show us what the direction is. But I like to use the angle. All right, that's example 5 done, or example 1. Example 1. All right, let's do example 2, which is in this little lesson, example 6. All right, so my mission is going to be for part A to find the equation of the tangent line. Now t equals -1. Okay, well, there are two things I need for an equation of the tangent line, right? I need a point, and I need a slope. All right, to find the point, what do we do? Well, I know t is equal to -1, and this is the position vector pointing to where I will be at t equals 1 if it's in standard position, and we'll put it in standard position. So I need r of -1. And that's going to be giving me a position vector pointing somewhere. All right, so what happens when I plug in -1? Let's see if I can do this math in public. This is -2 minus 3, which is -5. And then if I plug -1 in here, I get -1 minus plus 12, which is 11. All right. Let's see. Does that work out in our own mind? Let's try again. -1 minus, yeah, I feel good about that actually. All right, the slope. So this means the point is -5, 11, because this position function is pointing at this point. And the slope is going to be dy dx is equal to dy dt over dx dt. Well, I don't know what those two things are, so let's figure out what the velocity vector is. Well, it's just the derivative of the component parts, which would be that's 6t squared minus 6t, comma, 3t squared minus 12. All right? And I want the velocity at -1, so I can have the component parts to put in here for the slope. All right, so what happens now when I want to find the slope? So let's plug in -1. And what do we get when we plug in -1? Well, let's see, we get 6 plus 6 is 12. And then we plug in -1 and we get 3 minus 12, which is -9. So then these component parts over each other are going to be -9 over 12, which is going to be equal to -3/4 if I reduce it. So the tangent line is going to be y minus 11 equals the slope, which is -3/4 times x plus 5. And that's the tangent line to this curve at t equals -1. All right. All right, so we're going to do this on the calculator to see if we're right. So diamond y equals, I'm going to deselect these by pressing F4, and then we're going to put our new curve in here, which is going to be 2t to the third minus 3t squared. And then we're going to put in our other curve, which is t to the third minus 12t. All right, and then I'm going to change my window around a little bit. So let's see, because this is, I think, way too big. So let's, we're going to start at 0 and we'll go to 20. And t-step is fine. I'm going to make this -5. And then we'll make x max 20. That's fine. And then y min and y max. I don't know. Let's see what happens when we look at this graph. I don't see all of it down here, so I need to change the window in the y min department. So let's make this -30, because I know there's more to the curve than that. There it is. Okay, which is pretty cool. And at t equals -1, let's see, diamond. I want you to look, or sorry, I want you to look at the math features here. So we're going to go F5, and I want you to notice, do you see how it says you can find the value of your function when t is equal to, so let's press enter, -1. Oop. You know why I can't do that? Because I don't have -1 on my t max. So let's change the window to -3. We got to show that curve. Okay, there it is. It's graphing. -5, 11. That's where my point is. So I probably need to change my window again in the x min. Let's make this -10, and then the y max needs to be at least 15 so we can see that curve. Okay, here we go. There's the graph. All right, so we're going to go F5, find the value. Whoops, it's still graphing. Sorry, it's busy. I'm getting ahead of myself here. All right, so F5, and we're going to do the value of our function when t is -1. And we see that it's -511, so hallelujah, we were right. And does it look like I have a slope of -3/4 here? The answer is yes. Now, what's really cool about this calculator is if we go back to F5, I want you to notice there's a derivatives thing on the menu here, and we can, you notice that it says dy dx, dy dt, and dx dt. All right, I want dy dx, right, because that's what we just tried to find, and I want it at -1. And you see how it gave us a slope of 0.75? Very cool. And so you can see easily enough that the slope is -0.75, and it works beautifully. Very nice. Okay, the next thing that's interesting about this curve is where we might have vertical or horizontal tangent lines. So how do we find that? Horizontal tangent lines. Well, that's when the the dy dt is equal to 0. So dy dt, which we found out right here, was 3t squared is equal to 3t squared minus 12. We're going to set that equal to 0. I'm going to factor out a 3, and I get t squared minus 4 equals 0. So 3 times t minus 2, t plus 2 equals 0. We get t equals -2 and 2. Can't see what I'm writing. I'm really sorry about that. Okay. And so we're going to say we have horizontal tangents when t equals -2 and 2. If I wanted to know what the equations of those lines were, what would I have to do? Well, since they're horizontals, I need to plug them back into the y component. I'd have to plug them back in here. So I would say at t equals 2, we have a horizontal line at, that's going to be 8. 8 minus 24, which would be -16. So it's going to be y equals -16. And at t equals -2, it's going to be y equals, what happens is this? I'm going to have a -8, and that's going to be a plus 24, right? So that'll be at y equals 16, I think. So we're going to find out. We're going to verify that. And I can tell you right now that my window is not big enough to see the y equals 16. So let's make this y max 20. And it's going to take a second to regraph it, but we're going to verify it. All right. It's thinking, it needs to hurry. All right, so F5, I want to find the derivative when dy dt is at -2. Guess what? That's 0. That's a 0 slope. And that's going to be somewhere over there. Fascinating. Well, I'd like to see it, though. Anyway, F5, let's do the value at t equals -2. Well, we know that's 16. We can see that it's 16. Oh, and the x is at -28. So it's way the heck over here. Well, that's why I'm not seeing it. I'll make this 30. All right, so F5. I'm rushing it. I'm rushing the computer, the calculator. There you go. F5 when my value when t is -2. Well, it's not showing it on here, but it's over here. And I'm sure you can see that that's a horizontal tangent over here. And then down here, I'm wondering if we can, I don't know how to graph the tangent line at the same time. That's going to be a story for another show. All right. But we have a horizontal tangent here at -16 as well. All right, or just do F5, value my function when t is 2. See, now it's showing it here. That's weird. But that's where the horizontal tangent is. Now I can find the vertical tangent by setting dx dt equal to 0 and figuring out where that is. And we're going to have two locations. We're going to have it when it's 0 here, and then we're going to have it when it's another number. So let's find the vertical tangent. That occurs when dx dt is equal to 0. And that's going to be dx dt was 6t squared minus 6t equals 0. We can factor out a 6t, and we get t minus 1 equals 0. And so that's going to be t equals 0 and t equals 1. And that's where our vertical lines are going to be. And the vertical lines will be at x equals 0. I'm sorry, when t equals 0. T equals 0, I go back to my position function, which happens to be right here, and I plug in 0 and I get 0. So at x equals 0, and then at x equals, t equals 1, my x value is going to be -1. So x equals -1. And if you look at this curve, you can see that we have vertical tangents at 0 and at -1. Pretty simple to see that. All right. So we have found the velocity vector, the acceleration vector. We have found the speed and the acceleration, and we have now found the tangent line and the horizontal tangent line and the vertical tangent lines to the curve. Okay. What we have not talked about is when a function is speeding up or slowing down. All right. Now, I really like to do this exploration, and this is the path of a pendulum. And think of a pendulum as something that's going around and creating a path with the tip of the pendulum. There are a lot of famous ones that you can go visit. There's one in Los Angeles, and at their observatory, and it's really cool to see the path of the tip of the pendulum rotate. But this is the path of the end of a pendulum swinging, and it's given by this set of parametric equations. So I'm going to write my position function as r of t equals 5 cosine of 0.8t and 3 times the sine of 0.8t. All right, and the first question says, let's find the dx dt and dy dt when t is 1. Well, that's just asking us to find the velocity. And the velocity is just the derivative of the position vector. So that's going to be, and 0.8, believe it or not, is equal to 4/5. So this is going to be -4/5 because I got to take the derivative of the inside. So -4 times the sine, because the 5's cancel, of 0.8t. And then this is going to be 4/5 times 3, which is 12/5 times the cosine of 0.8t if I were to take the derivative of those components. And if I want to find the velocity evaluated at 1, we're going to do that. And I'm going to do that on the calculator. Okay, so we're going to go diamond y equals. And I want you to please notice, I'm going to deselect these two. what is the function value here? It's going to be xt3 of t and yt3 of t. And it's good to remember this because then we can do the evaluation of this vector on the front of on the home screen, okay? So I'm going to plug those in. So we're going to plug in a -4. Okay, sorry, escape. -4 times the sine, second sine of 0.8 t, and that's the x component, and the y component is 12 divided by 5 times second cosine 0.8 t. All right, and now I'm going to go to the home screen. And how do we enter vectors in the calculator? This is a very quick lesson on how to enter vectors in the calculator. I want you to notice these brackets up here above the comma and the divide bar. Do you see this is a closed bracket? So to do a vector, you just do second closed bracket because they don't have the angular brackets on here. So we're going to do that, and then we're going to type in -4 second sine 0.8 t, because that's the first component, comma, the second component, which is 12 divided by 5, second cosine of 0.8 t. I hesitated there for a minute because you know the cosine is always the x, but not in this case. All right, so I'm going to close my brackets by going second divide. And there it is. So there's my vector. So it's got a vector in there, but I want it evaluated at 1. So I'm going to go to the end, and I'm going to go such that t equals 1. And press enter. And it gives us our velocity vector at 1, which is -2.869. -2.869. And remember, in AP Calculus, we need how many decimals? 3. And then 1.672. 1.672. All right, so that's part 1 done. Okay, part 2 says the derivatives in problem 1 are the velocity of the pendulum in the x and the y directions. On the figure, construct the vectors of lengths dx and dy in the x and y directive, respectively, starting at the point on the graph where t is 1. Okay, and then I'm going to do part 3 at the same time here, which is to draw the position vector. Okay, so the position vector at t equals 1 is pointing to where we're standing at t equals 1, and that's where the pendulum is at t equals 1. So this right here is r of 1. Okay, now I'm going to graph the velocity vector. The velocity vector I'm going to put at the tip of the position vector, and that's going to be -2.8 roughly to the left and up 1.672. That's where the tip's going to go. So we're going to go left about, that's 2.8 roughly, and that's just an estimation, and then up 1.6. So we're going to go up about 1.6 right here. So that's going to be the tip. So pardon me if I turn this to graph this. And there is the velocity vector at 1. Okay, now the question's asking us, what relationship does this vector have to the graph? If I put them in the summing position, right? Because when we add two vectors together graphically, we put the tail of one vector on the tip of the other. Okay, and when we do that, we get an addition situation. And what does this relationship have a graph? What they want you to notice is the velocity vector is tangential to the path. So we're going to say the velocity at 1 is tangent to the path at t equals 1, which is pretty cool. Okay, now we're going to see what the relationship is with the acceleration. All right, so let's find the acceleration vector, which means I'm going to take the derivative of the velocity vector, which is negative 4/5 times negative 4, which is going to be negative 16 over 5 cosine of 0.8t. And then negative 4/5 times this, which would be negative 48 over 25 times the sine of 0.8t. Now I'm going to check myself because I'm on video and I might be wrong. So, not that that's ever happened. Anyway, okay, so the derivative of negative 4 sine of 0.8t is going to be 4/5, which is the derivative of the inside, times this 4, which is negative 16 over 5. I like that, cosine of 0.8t. And then 4/5 times the derivative of cosine, which is negative, so that's negative 48 over 25. Yep, I like that derivative. I like it very much. All right, but I'm going to show you now how to take the derivative of a vector on your calculator, because we have our vector stored, don't we, for the velocity, don't we? The velocity vector as a function of time is right here. So how do we take derivatives with a calculator? Well, we can either hit F3 derivative, or we can go second, number 8. I want you to notice there's a D here. So second number 8, and I'm going to go up and I'm going to grab my velocity vector, bring it down, and I'm going to go comma. What do I want to take the derivative with respect to? Well, I want to take it with respect to t, and then I'm going to close the derivative, and there it is. It's going to give me my velocity vector. My acceleration vector, which is very, very cool. And so this is negative 3.2, which certainly looks like negative 16 over 5. And then I'm sure that negative 1.92 is going to be negative 48 over 25. Okay, but I want the acceleration vector evaluated at 1. So we're going to go such that at the very end, t equals 1. And we're going to get a number. Did everybody see that? What's that number? It's negative 2.229 and negative 1.377. And I'm going to do the same thing with my graph here, except now I'm going to want a green color to be just a little bit different. Grab my green for my vector here. I'm going to put the acceleration vector here on the graph where its tail is on the tip of the position vector, and we're going to see how these work together. Okay, so I'm going to go left, negative 2.2, roughly, so 1, 2, and then 0.2 maybe put me right here, roughly. This is very rough. And then we're going to go down 1.4. So 1.4, maybe right about here. This is a guess. Okay, there we go. There's my acceleration vector evaluated at 1. Okay. So there we go. And I have the velocity and the acceleration on there. Now the question is, what is the particle doing? Is it speeding up or slowing down? Well, how do we know? Well, this is the answer right here. And I got to get another fun color here. How about purple? This angle here between the velocity and the acceleration, I'm going to call theta. This angle is going to tell us whether it's speeding up or slowing down. Okay? And I'm going to give you a hint. My best friend, Mr. Forrester, says in his book, sketch a figure when the velocity and acceleration, what they might look like if the object is slowing down. Okay, well, so the first thing is when you are sketching velocity, velocity is tangential to the curve. So here we go. Here's velocity. I'm going to grab velocity. Whoops, that was a bad move. And I did it in very green. Needs to be more tangential here. That's velocity. Okay? If it's slowing down, if your particle is slowing down, then the acceleration, which always points inwards towards the concavity, the acceleration is going to be this direction if it's slowing down, where this theta is, when theta is greater than 90 degrees. That means they're working against each other. Okay, and if I were to find the component parts, the resultant of this vector would be showing that it's slowing down. They're working against each other. What about if I have them speeding up? So I'm going to do another tangential. Here it is. I did a better job with that tangential. And then I have speeding up. That means the acceleration, which is pointing inward, and they're working together now. And they're working more in the same direction here. So what does that mean? Theta is less than 90. So you have an acute angle. All right. And then what happens if the velocity is constant? Well, you have a tangential vector, and then your acceleration is perpendicular to your velocity. So theta equals 90 degrees. So this situation is slowing down. This one is speeding up. And this one is constant velocity. All right, that's how you know. So let's look at our picture again. Is our vector angle between the velocity and the acceleration greater than 0, less than 0, or equal to 0? I mean, greater than 90, less than 90, or equal to 90? The answer is less than 90. So this is an acute angle, which means my particle is speeding up. Since theta, which is the angle between, is less than 90 degrees. And we could prove that by, how do we find the cosine of an angle between two vectors? We dot them together, right? And I'm going to write the velocity. So we would dot the velocity times the acceleration, and we would divide by their magnitudes. And if this is greater than 0, then it's a positive angle, or an acute angle. If it's less than 0, when the cosine is less than 0, think about it, right? If cosine is greater than 0 in this quadrant, and cosine theta is less than 0 in this quadrant. And we would have an acute angle here, and we would have, that would be an acute angle, and then we'd have an obtuse angle here if cosine of theta was less than 0. So we know that the particle is speeding up because the angle between them is less than 90 degrees. And this is the relationship, which I think is really cool. And remember that the velocity vector is always tangential to the path, and the position vector always points to where your particle is at time t on the path, and this vector is always rotating. And the acceleration is always pointing inward, and we just proved that by, coming up with the acceleration vector to show that it's pointing inward. Inward, the concavity is this way, so the acceleration is going to be pointing inward. Okay, so I think that's enough for this one video. It's a long one again, I'm sorry, but it's better than the first one I did. You guys have a great day.